Okay, so can you guys see my screen now?
Yes, sir.
All right. So we only have one topic for today. So I hope we can finish this one real quick, like basically part one and part two only, okay, so that we can have enough time to finish our quiz later on. All right. So is there anyone here who has an idea what is a Zener diode? So I'll be counting 5 seconds. If no one answered, then meaning no one has an idea about Zener diode. So five, four, three, two, one.
Sir, it allows I think backwards ba? Backward flow, sir?
Yeah. So in conventional diode or an ideal diode, so it will only allow the current if it's forward bias, right? But in reverse bias, it won't allow a current at all. But in Zener diode, this is a special purpose diode wherein it has a breakdown voltage. So once it reached that so-called breakdown voltage, okay, current now will be able to pass through that diode. So the same function with the forward bias, but with the reverse bias, so it has a special functionality. Okay. So you are actually correct, Mr. Racer. So very good on that one. All right. So without a further delay, let me show to you what is really a Zener diode. All right. So Zener diode is a special type diode which behaves just like a normal general purpose diode, just like what we have before. A silicon diode. So this one is actually consisting of silicon PN junction, same, and when biased in forward direction. However, as soon as the reverse voltage reaches a predetermined value, so this predetermined value is depending on the breakdown voltage of that certain diode or that certain Zener diode. So it could be at 4 volts, 6 volts, 10 volts, 12 volts, 50 volts, or 100 volts. So that depends on the Zener diode itself. So the Zener diode begins to conduct, okay, in the reverse direction, which is called the Zener voltage, right? So in forward bias, it works normally, just like our normal general purpose diode. But in reverse diode, let's say our breakdown voltage is 10 volts. So it will not accept, okay, it will not accept a negative up to -9. Okay. But once it reached -10, okay, that is the time that it will now start to conduct a current. Okay. So this one is especially only for the reverse direction or reverse bias. But if it's forward bias, then it will work as a normal diode. Okay. So this is because when the reverse voltage applied across the sun diode exceeds the rated voltage or the so-called predetermined value or the avalanche breakdown or designer voltage. So we have a lot of uh, namings on that one. So we can call that one avalanche breakdown, wherein once it occurs in the semiconductor depletion layer, and a current starts to flow through the diode to limit this increase in voltage. Okay. In other words, it is specially designed to reverse breakdown voltage. Okay. If it's in forward bias, it works the same with our diode or with our normal diode. So this one should function, okay, or you should use this one in reverse bias only or reverse breakdown voltage, okay, which takes advantage of any reverse voltage applied to it. So as you can see right here in forward bias, so let's say this is our voltage threshold, wherein if it's silicon, it won't give us or it won't allow a current unless it consumes 0.7 volts. So it is the same with our reverse bias at a certain point, okay, wherein it will not conduct unless it reach the breakdown voltage or the avalanche breakdown. Okay, so at this point, maybe this is its predetermined value wherein it's going to break down. So this one now, or at this point, it will now start to conduct current. Okay, so let's say maybe this one is up to 3 volts. And then once it exceeded 3 volts, let's say 4 volts, then it will now conduct a current. Okay, so I hope this one is clear. So again, this one is the same with our normal diode. It's just that it has to work on the reverse bias, wherein with a predetermined value. Okay, so just a continuation. So this is just a short example or a quick example how to show to you how it has a Zener diagram. So letter A here is the reverse bias. Okay, silicon small signal diode breaks down at 100 volts. So we have a diode here wherein it's silicon, and then it says here that its breakdown voltage is 100 volts, right? And then letter B here is a symbol for Zener diode. Actually, this one is a diode wherein it has this one. Okay, actually in reality, they have the same. Okay, they have the same physical characteristics. But for us to be able to identify whether this one is a normal diode or a Zener diode, so they've included like this additional symbol, wherein instead of a horizontal line only, it has a mini curve here and then a mini going up a line there. So it's like that. It's like this. Okay. So I don't know how to uh, explain this one, but this is the symbol for the Zener diode. So in cathode area, so it has an additional layer or drawing. Okay, like this one. Okay. So memorize that one. So this is the symbol of a Zener diode, and then this one is just a normal diode. Okay. All right. So without further delay, so unfortunately, when normal rectifying diodes break down, they usually do destructively. Okay, this one is with normal diodes. However, it is possible to build a special type of diode that can handle breakdown without failing completely. Because normally, if it's a normal diode, at some point, once it's reached its limit, okay, it might get destroyed or it might not work properly anymore, or worse is it might get burned. Okay, seem like being destroyed. So yeah, but having a Zener diode is the solution. Okay, let's say it already reaching this breakdown voltage, then that's the time that it will allow to pass through that current. Right? So this type of diode is called the Zener diode, and its symbol is shown in the figure B above this one. Okay, so when for bias, Zener diodes behave much the same as standard rectifying diodes. So they have a forward voltage drop which allows the diode equation and is about 0.7 volts. Okay, that is during the forward bias. In reverse bias mode, they do not conduct until the applied voltage reaches or exceeds the so-called Zener voltage. Okay, at which point the diode is able to conduct substantial current, and in doing so, we'll try to limit the voltage drop across it to the or to that Zener voltage point. So if you're going to take a look on this one, we have a voltage source of 150 volts. And then we have here a Zener diode, okay, wherein it will break down at exactly 100 volts. So imagine this one as in it will not completely conduct 0 to 100 volts. But once it exceeds or once voltage is equal, okay, so it should be equal at least, okay, to our Zener breakdown voltage. So it will conduct at exactly 101 volts or 100 volts and above. So that is why you can see right here that the remaining voltage is 50 volts because that's the voltage that is circulating in our circuit now. Okay, so 0 to 99, it won't conduct. Okay, and then 100 and above, that is now the time that it will conduct. So the remaining voltage is 50 volts. So 100 150 minus 100 is 50 volts. So I hope you guys get the idea already. So any question or clarification so far? It's an answer coming from Mr. Eda. So let me just recap this one again. So this predetermined voltage is random. Okay, not really random. Could be any value. Okay, so it could be 1 volt, 2 volts, 3 volts, or literally any value. So that depends on me. Okay, on what predetermined voltage or what Zener breakdown voltage that I will put in here. Okay, so imagine this one as another external voltage. Okay, wherein it's just there, wherein if a voltage passes through here, so you have to deduct this one. So for us to be able to have a complete working Zener diode circuit, our voltage source must be always greater than our Zener breakdown voltage. Okay, so if we have here 99, okay, 99 volts of voltage source. So if it tries to pass through this one, so it won't be able to activate this diode because its breakdown voltage is 100. So as a result, this circuit will become off. Okay, so it's off. So positive or negative, it's off during the reverse bias, but it's on during the forward bias because it's work the same with our normal diode. So as you can see, this one should be always greater than our Zener voltage breakdown. All right, so let's have an example. So find the V out and dual currents during the positive and negative half cycle of the circuit. So consider that as an ideal Zener diode. Okay, so this one is not a silicon, just an ideal. So as you can see right here, we have a voltage source of 3 volts, and then we have a Zener diode in here, wherein its breakdown voltage is 5 volts. So, a quick question. So during the negative, during the reverse bias, okay, will it conduct or no? Will this allow a current or our voltage, or is our voltage source enough to make this Zener diode turn on? Hello guys, you guys still there? Or what is our current in this circuit? So coming from Mr. Duman, no. So yes, you are right. So as you can see, 3 volts is lesser than 5 volts. Yes, yes. So coming from Mr. Uh, Gulaidan, so no sir kasi the abot's 5, yes. 3 volts is not enough to break down the voltage that is required in the Zener diode, okay, which is 5 volts and above. 3 volts is lesser than 5, so in reverse bias, we have 0 current, okay. And then of course, there is no V out since our 3 volts wasn't able to, wasn't able to pass through this path. Okay, this one's like an open circuit already. And during the negative half cycle, which is, negative is connected to the negative, and then positive is connected to the positive. So it is a forward bias, right? So as usual, it works normally as a normal diode. So it will now allow to pass through a current completely. So our V out is negative 3 volts. And then our total current in this circuit is negative 3 milliamps. So just use the Ohm's law. I is equal to V divided by R. So negative 3 divided by 1K. Okay, so we only have one resistance. So negative 3 divided by 1K is negative 3 milliampere. All right. So that's the answer or solution for the example number 1. Any questions so far? Is it clear so far? So this is very crucial. At this point, you should already, you know, having a clear idea on how a Zener diet works. Okay, because the more that you're not, uh, the more that you were not understanding our topic, the more it's difficult for you to analyze the next examples. All right, so that's a good thing that most of you uh, doesn't have a question or it's clear to you guys. So let's move on. So we have another example, okay, which is same everything except with our voltage source. So the same question also, find the Vouts and total currents during the positive and negative half cycle of the circuit. And then also consider that as an ideal Zener diode. So I'll give you guys 30 seconds to think what is our V out during the positive cycle, and then what is our V out during the negative half cycle. So feel free to use our chat box. And if you want to include the current during the positive and negative, then better. And then we will see later on if your answer is correct or not. Is there anyone who's trying to answer this one? Delay ka yata, Mr. Ramos ah. So, number 2 na tayo. Alright. What is that 9, sir? Miss Daryl. Is that during the positive or during the negative? Yung positive. Alright. So, how about during the negative half cycle? Miss Daryl, are you still there? Negative 14. Alright. So, inunahan ka ni Mr. Wilmer. So, coming from Mr. Escobar, so if it's or during the negative half cycle, it's negative 40 volts, which is correct. Okay, so during the positive half cycle, wherein positive is connected to the negative or the cathode, and the negative is connected to the positive or the anode, which will make this one a reverse bias. So again, if it's reverse bias, so we have to check what is the breakdown voltage. So our breakdown voltage is 5 volts. So we have to check whether this one is higher than the breakdown voltage. So yes, voltage source is higher than the breakdown voltage. So as you can see, 14 is greater than 5. So for you to be able to get the voltage output, so just simply deduct this one. Okay. So 14 minus 5 is 9 volts. Okay, so that is our V out during the positive half cycle, which make this one a reverse bias. And then during the negative half cycle, so as you can see, negative is connected to the negative, positive is connected to the positive, which will make this one a forward bias. So if it's in forward bias, so it works as a general normal diode. Okay. So since this one is ideal, then we don't have to deduct any voltage from there. So it will completely become a closed circuit. So our V out is negative 14 volts. So here's the solution for number 2. Okay, so during the positive, we have the 9 volts. And then here's the total current at that point. So during the positive half cycle, we have 9 milliamps. And then during the negative half cycle, we have negative 14 volts. And then, of course, just change this one. And then we still have the same divisor, which is 1K, which is the total resistance. So negative 14 divided by 1K is negative 14 milliamps. All right, so is it clear so far, guys? Are you guys now getting the main idea on how to use a Zener diode, or on how does a Zener diode work? Your poster. All right, so it's good. What about the others? Maybe you guys have a question or a clarification.
Clear, sir.
All right, it's good. So count 3 seconds for the others. 3, 2, 1. All right, so it seems that you guys still doesn't have a question. So let's move on. Okay, so we have this example number 3. Okay, so find the V out. So the same question. So find the V out and total current during the positive and negative half cycle of the circuit, and then consider the diode as an ideal Zener diode. So as you can see, we have bidirectional Zener diodes here. So we have two Zener diodes wherein their breakdown voltage is also the same. Okay, and then we have a voltage source of 30 volts. So I'll give you guys a minute to analyze this one, and then give me the answer on what is our V out during the positive, and then what is our V out during the negative half cycle. Okay, so start analyzing it. So this is an open recitation. Okay, as soon as you have your answer, feel free to put it in our chat box so that we can check your answer. Last 10 seconds. Right, so time is over. So uh just basically analyze it step by step. So 20 posters are positive. Yes, that one is correct. How about the negative? Or how about during the negative half cycle? All right, so negative 20, yeah. So Mr. Gulaidan is incorrect, or not correct. The correct answer is negative 20. So Miss Daryl got the correct answer. All right. So as you can see, during the positive half cycle, we have 20 volts. And then during the negative half cycle, we have negative 20 volts. Okay, so this one will like clip both sides. Okay, it's like clipper. So instead of having a 30 volts peak to peak, we have only a 20 volts on the positive half cycle, and then negative 20 volts during the negative half cycle. So how did that happen? So again, during the positive half cycle. So positive is connected to negative, and the negative is connected to the positive of the Zener diode 1. So as a result, this one will become a reverse bias. So again, we have to compare whether our voltage source is greater than the Zener breakdown voltage, which is true. Okay, 30 volts is greater than 10 volts. So if that's the case, then all you have to do is deduct the breakdown voltage to our voltage source. So 30 minus 10 is 20 volts. So at this point, okay, we already have a 20 volts. And then since we have here a sign of positive, so positive is connected to the positive and the negative is connected to the negative of the Zener diode 2. So as a result, this one will become a forward bias. So if it's a forward bias, it will the same with our normal diode, wherein it will allow to pass through a current. So if that's the case, then this one will become a closed circuit. So why closed circuit? Because that one is an ideal Zener diode, okay, or an ideal diode. So it will pass through this one. So as a result, we still have 20 volts. Okay, so during the positive half cycle, we have a 20 volts during the positive. And then during the negative half cycle, so as you can see, negative is connected to the negative, and then positive is connected to the positive, which will make the Zener diode 1 as a forward bias. Okay, so if that's the case, then this one will become a closed circuit. And then at this point, so negative now is connected to the positive, and then positive is connected to the negative, which will make this one again a reverse bias. Okay, so again, if that's the case, then we have to check whether the voltage source is greater than the breakdown voltage of the Zener diode or this certain Zener diode. So yes, it is true that our voltage source is greater than the breakdown voltage of Zener diode 2. So just simply deduct it. Okay. So 30 minus 10 is 20. So at this point, we have negative 20 volts. Okay. Because we have here negative 30 plus 10. So we have here negative 20 volts. So here's the solution. So 20 volts during the positive and then negative 20 volts during the negative. And then of course, the current is this one. So there is a private message coming from Mr. Escobar. Yes. So there is no zero point 0.7 deduction because as you can see right here, this one is an ideal Zener diode or an ideal diode. Okay. So it works the same with our conventional ideal diode. Right. So I hope I was able to answer your question. So here are their solutions. So is it clear so far, guys?
Yes.
All right, all right. Okay. So clear coming from Mr. Charles, clear coming from Mr. Raster, and then Mr. Duman says also it's clear. So I hope to the others who didn't answer. So it is also clear to you guys. Okay. So let's now move on. So we now have another kind of implementation of a Zener diode. So we have here a Zener diode as a voltage regulator. So how did this become a voltage regulator? So as you can see right here, we now have a parallel connection of our Zener diode. So before, we have a series connection. So our diode is on this one, and then our resistor is on this side, which, whatever is our voltage source, you have to deduct the voltage breakdown. But in here, okay, as you can see, in parallel, whatever is a voltage drop, okay, in this uh, Zener diode, that is our voltage output already, okay, because that's how uh, we calculate, okay, the V out on the parallel circuit, okay. So in here, as long as our voltage input is greater than VZ, okay, or the Zener diode voltage, so this one will work perfectly. Okay, we have a regulated voltage. So why regulated voltage? Because whatever is the voltage or the breakdown voltage on this one, or the voltage drop on this Zener diode, that is already our V out. So let's say we have here 5 volts, and then we have 10 volts in the voltage source. So 10 volts is greater than 5 volts. So our V out is 5 volts. Okay, whatever is the breakdown voltage on this Zener diode. We have 20 volts, we still have the same 5 volts as a V out. If we have 100 volts, we still have the same 5 volts as our V out. If we have 1 million volts, still the same. We still have a 5 volts V out, right? So as you can see, our voltage now was regulated into the voltage or the breakdown voltage of our Zener diode, right? So that is why we call this one as a voltage regulator. So whatever is the Zener voltage, that is now our regulated voltage, as long as the voltage source is higher than this one. Okay. So, Zener diodes can be used to produce stabilized voltage output with low ripple under varying load current conditions by passing a small current through the diode from a voltage source via a suitable current limiting RS. So the Zener diode will conduct sufficient current to maintain a voltage drop of P out. And then here are some of the uh, components that you have to consider. But we will discuss that one later on because we don't have enough time anymore. So again, just wait 5 to 7 minutes for our part 2. Okay, since yeah, I still have to convert the pre-recorded video. So goodbye for now. Just wait for our part 2. Alright, so I will end this one now. Again, just wait 5 to 7 minutes.